Welcome back, everybody. Please come in as fast as you can. So I'm very pleased to introduce Tim Palmer, who's a fellow Brit. He is a Royal Society professor at the University of Oxford, and he studies dynamics and predictability of weather, and he's a pioneer of probabilistic ensemble forecasting techniques. And he bridges between a deep understanding of theory and practical forecasting. And for many years, he worked at the European Weather Centre for Numerical Weather Prediction, ECMWF, which is the foremost medium-range weather prediction centre. Over to you.
Thank you, John. Thank you very much. Let's see, does that work? Yeah. Okay. I want to start by posing a kind of slight conundrum, I guess, which is that we have these two great figures who clearly their interests are very closely related. As has been mentioned, Jule was a founding father of numerical weather prediction. He led the team at Princeton that gave us the first numerical forecasts. Ed transformed our understanding of predictability of weather. And yet, I would say for many years, if not decades, there was very little interaction between, certainly between the two fields of science that these two pioneers created. And I want to discuss the reasons for that, but conclude on a more positive note and say that things are changing very rapidly in the last few years. Okay, so not working the gizmo right, okay. So just to review very briefly, this was indeed the team under von Neumann, who I suppose took the concept by Wilhelm Bjerknes, who's been mentioned, Lewis Fry Richardson in the UK, and maybe one or two others, that one can treat weather forecasting as a traditional scientific initial value problem. If we have enough observations to determine initial conditions, and if we know the equations of motion, which we do, then in principle we can determine some future state from that. But it was clearly obvious that to do this in any meaningful way, to advance predictions faster than the weather advanced themselves, we'd have to rely on technology that before the war didn't exist, and after the war started to exist, so digital computers. And from those first days, numerical weather prediction has really not looked back. My own institute, the UK Met Office, where I started to work in meteorology, embraced numerical methods in the 1960s. And around that time, people began to ask, well, how far ahead can we forecast the weather? And people like Kiku Miyakoda, for example, and others at GFDL and elsewhere, became clear that maybe around 10 days was a good sort of timescale to think about the practical limit of weather forecasting. So this notion of what's sometimes called a deterministic limit of numerical weather prediction began to arise. And the whole kind of concept underpinning the European Centre for Medium-Range Weather Forecast, which, as John said, I worked for many years, was based on trying to kind of realize this theoretical idea that we could predict weather 10 days ahead. A recent paper in Nature a couple of years ago, I think summarizes the whole evolution quite well, in that there has been, from those early 1950s, a revolution in this particular field. But it's been a kind of quiet revolution, and the public at large are probably not really aware of what has happened. It's been not only the sophistication of numerical weather predictions, of numerical weather prediction models, it's also about how satellite data has really transformed our ability to create accurate sets of initial conditions. And that's, by the way, illustrated on the right-hand graph, which shows how skill scores have been rising over the years, but it also shows how forecasts in the southern hemisphere, which were traditionally much poorer than in the northern hemisphere, have become pretty much the same level of skill. So those colors disappearing means that there's no real difference between forecast skill in the northern and southern hemisphere. And that's just basically due to satellite data. And that, by the way, has needed very sophisticated algorithms to actually assimilate that data into the model. So it's all very, I would say, encouraging, and it's a nice story. But, you know, as everyone knows, there's an Achilles heel in this type of weather prediction. And that is that sometimes it goes wrong. And when it goes wrong, it attracts the derision and ridicule of public and media alike. And I want to focus, I mean, you can, on this side of the pond, you have lots of examples, no doubt. I'm going to just focus on one on my side. So this is a very famous event for those of us who lived through it. It famously, this is a storm that famously reduced the town of Sevenoaks in Kent to no oaks, and caused untold damage, you know, across the whole of southern England, which I'll show you, but was completely misforecast. Even the night before, it hits in the early hours of the morning, even the night before, the forecasters were just talking about a little bit breezy the next day. So this is an example of the derision and ridicule that the poor forecasters had to endure. This is the main BBC anchorman the next morning. You chaps are a fat lot of good last night. If you can't forecast the worst storms for several centuries, 3 hours before they happen, what are you doing? Well, meteorologists are a kind of a resourceful lot, and the Met Office made hay out of this by saying to government, we need much bigger computers so we can increase our resolution of our models and make much better forecasts. This argument has been used many times, maybe not that long ago in another case. So there we are. So I just want to let that hanging now for just a few minutes and move on to talk about Lorenz. So just leave that as a hanging issue. As Kerry very nicely mentioned, Ed showed how, with a very simple system, deterministic forecasts would decorrelate. I don't know if this works. Yes, there we are. So here's an animation of two trajectories of Lorenz 63, which look like they're the same for a while, but then completely decorrelate. And as Kerry said, you know, Ed's motivation was basically to show that simple statistical methods, like analog methods, find an analog of the current month and use next month's from the analog to forecast the weather for next month. These were doomed to failure. So I got involved in this type of work in the early 1980s. Joe Pedlosky had talked about Jim Holton. I'd actually been working with Jim Holton on stratospheric dynamics at the University of Washington. And the vagaries of the Met Office in those days were that Jim Holton wrote me a nice letter of reference. So I immediately then, as a result of that, got posted out of the stratospheric branch to the long-range forecasting branch, about which I knew absolutely nothing. So I had to absorb what was going on. And what was going on in long range, so this is 30-day forecasting, was that people had taken aboard Lorenz's message. And the models were, they were empirical models of the type Kerry mentioned, but the output was probabilistic. And for example, the models my colleagues in that branch worked with would predict probabilities for different types of weather regimes. What then were called Lamb weather types, but these were what today we would call regimes. And these would be given to utility companies, energy, water, gas, and so on, in terms of the next month's weather is in probabilities. So my job was to try to bring numerical weather prediction models into this milieu, if you like. And I was aware, for example, of the work of Shukla, who's in the audience, and again, Mia Koda, showing how maybe, you know, numerical models could play a valuable role in monthly forecasting. But the problem was to get it into a state where it could be used, blended with these probabilistic empirical models. So from that point of view, it was obvious that what we had to do was run ensembles, run from consecutive analyses, if you like, 12-hour analyses, produce ensembles, I think there were about 9 members long, look at weather regimes within those ensembles, and produce probabilities. and then merge those into the statistical ones. So this was completely, this was non-controversial. I mean, everybody said, this is fine, this is obvious, this is what we should do. In a journal which is no longer functioning, the Meteorological Magazine, we described our first operational ensemble forecast in November 1985. Now, so at the end of the 80s, there's this real kind of brick wall between the numerical weather prediction on timescales of less than 10 days and these probabilistic methods which combined empirical statistical models and the emerging idea of ensemble forecasting on the monthly timescale, and very little interaction between them. But it became obvious to me that this brick wall was very artificial and didn't actually make much sense. And Lorenz's model is actually a very good way to illustrate the concept. So what we're looking at here are, let's call them short-range forecasts from Lorenz 63, where we're not just running a single trajectory, but a little ball, if you like, or a little sphere, or something like that, of initial conditions. Now, the top left is something that you might say is fairly typical on those timescales, which is that there is actually very little divergence of trajectories. So this notion of exponential divergence is not something that happens all the time for all the initial conditions. The top right is one where you start to see some growth of uncertainty, but it's still kind of manageable. But then, and this is the crucial point, there are initial conditions where the butterfly effect really hits you hard, even within this timescale where you think things are deterministic. So that's the bottom figure. This is characteristic of a nonlinear system. It's just as simple as that. In a nonlinear system, the growth of initial perturbations will be dependent on the state you start from. So I've always felt this notion of a deterministic limit was a little bit of a misleading concept, and it's sort of prevented the sort of synthesis of Ed's ideas into these shorter timescales where they would apply. Now, this really is a good example of the bottom one is a very good example of the October storm. And in fact, in more recent years, we've rerun retrospectively the October 87 storm with a modern ensemble forecast from ECMWF, incidentally using very high resolution models, so the things that the Met Office thought were necessary to kind of correct it. And what you actually see from these 50 so-called postage stamp maps, all started from almost identical initial conditions, was that they have diverged phenomenally after 2 days. This is a completely exceptional type of situation where you get almost any synoptic weather type you can think of. Just look at those two neighboring ones. This is over the UK here. So what was the reaction to this? A lot of people said, this is interesting theoretically, but completely useless, because this is giving forecasters too much information. It's information overload. They'll never be able to deal with that. And in fact, they said, what we should do, if you're going to use this type of technique, we should average these 50 forecasts together, produce an ensemble mean. You can formally show, actually, the ensemble mean over a large number of forecasts actually has a lower RMS error than the individual members. But it's pretty obvious you're throwing the baby out with the bathwater. You're smoothing these 50 maps. You'll no longer have a severe weather event. So this is a useless idea, in my view. Rather, we need to synthesize things in terms of probability. And this is a simple sort of statistic you can get from these 50 members, which is a probability of hurricane force gusts on that morning of October the 16th. And these probabilities are around, 30 or 40%. And given that hurricanes, given that in Hertfordshire, Herefordshire, and Hampshire, hurricanes hardly ever happen, 30 or 40% is a rather large number by climatological. Well, Sevenoaks is just in Kent, so somewhere down here, roughly. So it's actually on that swath. Okay. By the way, the other argument that people say, well, you're taking away resources that should be used to increase the resolution of the models. is also bogus, because if anything, increasing the resolution of the models is going to make this divergence even sharper. It's going to even expose this instability even more. So, if I can get this to work. So we developed ensemble forecasting. Eugenia and Zoltan Toth at NCEP had a kind of parallel program going on, and we both became operational in 1992. Now, I've got some sort of technical stuff here, which I'm running out of time, but I want to mention in the context of Ed and Jule. If you introduce butterflies, numerical butterflies into the model by perturbing grid points, with noise which is spatially uncorrelated, you don't see the butterfly effect at all. All that happens is the model's diffusion on those scales, numerical diffusion, just kills the perturbation off. So you have to be actually quite clever to introduce perturbations, initial perturbations, which are going to have the growth characteristics that you want. Eugenia and I pursued slightly different philosophies, and I wish I had more time to talk about that, but we focused on a thing called singular vectors, which was actually very much motivated by the work of Brian Farrell, who was a student of Dick Lindzen, who's here. And Brian Farrell actually did a lot of his work looking at the Charney baroclinic instability problem and analyzing finite time growth of perturbations. And because these are technically non-Sturm-Liouville types of problems, you can get over finite times growth rates which vastly exceed the long-term exponential growth of the normal modes. Now, the thing I want to just mention is that I gave a talk about this when Ed was in the audience, and he came up to me afterwards and said, "Oh, this is really interesting, and I've learned a lot from your lecture." And then some years later, I was looking at his Lorenz paper in Tellus in 1985, and he talks about pretty much the same thing. These singular vectors are basically eigenvectors of, if you have a dynamical operator A, the singular vectors are eigenvectors of this product matrix. And in this paper, he's talking about eigenvalues and eigenvectors of this thing, giving you preferred configurations in the error field, and one could choose only a small number of these error fields from this calculation for superposition. Holy cow, he's completely trumped me I don't know. Actually, I think I got that's a typo. That should have been 65. Sorry, that's 65. So decades before. And the other area where we put a lot of work into represent model error is stochastic parametrization. And again, I gave a talk on this. Ed said, "Oh, that's really interesting. I've learned a lot from that talk." And then I looked back in his paper in 75. I believe that the ultimate climate models will be stochastic, i.e. random numbers will appear somewhere in the time derivative. So Ed was an amazing character. I'm conscious of the time. So ensemble forecasting, I think we've finally broken this brick wall down, and it exists on pretty much all timescales these days, from hours actually through to decades. This is a nice example of tropical cyclones, which again, like Ed's, like the Lorenz 63 ensembles, you can get very predictable ones, semi-predictable ones, and ones where that's actually got transposed by the computer, but that's a cyclone which it really doesn't know which way it's going. So, conscious of the time, I just want to finish with a couple of slides. I think the future, this is very encouraging from the point of view of societal impacts now. And one of the things I really think will be important in the future is how ensemble forecasting can really now provide objective criteria to decide, for example, whether emergency disaster preparedness agencies can start to be proactive before this is Haiyan. That was the example which I showed, which looked very predictable. And you think, well, why aren't they going in there in advance with their emergency shelters and food and so on? And the answer, of course, is that if it didn't happen, if the event didn't happen, it's very costly to go out. But with ensemble forecasting now, you can define objectively decision theoretic criteria. If you know the cost of preventative action, if you know how much loss you're saving by taking preventative action, and crucially, if you know the probability that the event will occur, you can form an objective criterion for taking that proactive action. And I'm sure we'll see a lot more of that in the future. So I'm finish with this slide just to say that I think after quite some time of largely independent development, work of these two giants of meteorology is really now seamlessly intertwined, and it's for the benefit not only of our science, but society more generally. Thank you.
Thank you very much.
So while Dick Linson is on now, we can take one question as Dick comes up. Anybody like to ask a question? Ray?
Back in the 80s, a lot of the error in medium-range weather forecasts was really still dominated by systematic error. And I wonder, as the computers have gotten bigger, is that still the case, or has the systematic bias gone away?
The large-scale systematic bias has really gone down a lot. But of course, there are still important systematic errors on smaller timescales. So for example, just getting intense rainfall amounts correctly simulated is still, models tend to somewhat underdo that. So actually, having to some extent won the Ensemble war, I am actually now and I used to not be, but having won the Ensemble war, I am actually now a great advocate that we should be putting resources into increasing model resolution. So to get those last few systematic errors right down.